Welcome to my new lecture about NMR spectroscopy. And through this video, I am going to discuss about the basic aspects of NMR spectroscopy. Nuclear magnetic resonance spectroscopy is a nuclei-specific spectroscopy. And NMR uses a large magnet to probe the intrinsic spin properties of atomic nuclei. Like all spectroscopies, NMR uses a component of electromagnetic radiation, that is radio waves, to promote the transitions between nuclear energy levels. So, the definition of NMR spectroscopy is that it is a technique which is based on the absorption of electromagnetic radiation in the radio frequency region of 4 to 900 MHz by nuclei of the atoms to induce transitions between nuclear energy level. Most chemists use NMR for the structure determination of small molecules. PMR H1 NMR is one of the NMR technique is mainly used for determining the number of hydrogen atoms in the compound. It is also used to study a variety of other nuclei such as nitrogen 15, fluorine 19, carbon 13 and phosphorus 31. The nucleus consists of elementary particles called neutrons and protons, which contain an intrinsic property called spin. Like electrons, the spin of the nucleus can be described using the quantum numbers, and here I, which is known as spin quantum number, it is the quantum number for nucleus. And from the table it is clear that atomic nuclei with even number of protons and nuclei have zero spin, and all other atoms with the odd number of atomic or mass numbers have non-zero spin. All nuclei with a non-zero spin have a magnetic moment and can be NMR active. And from the table it is clear that H1, whose atomic mass is odd as well as its atomic number is also odd, so it will have a non-zero I value and it is NMR active. But in the case of C12, which has an even atomic mass and even atomic number 6 and 12, so it will have a zero spin quantum number and it is not NMR active, or it is NMR inactive. Next we discuss about the theory of NMR spectroscopy. When a charged particle such as proton or any other which spin on its axis, it creates a magnetic field. So in the case of nucleus, which is positively charged, its spinning motion is also generate a magnetic field. So nucleus can be considered as a tiny bar magnet. Normally, tiny bar magnets are randomly oriented in space. However, in presence of a magnetic field B0, they are oriented with or against the applied field. And this figure shows that the orientation of a tiny bar magnet in the presence of magnetic field. Two orientations are possible. One is aligned with the applied field and other is aligned against the applied field B0. Likewise, the spinning motion of the nucleus also generate a magnetic field. And even in the absence of external magnetic field, a molecule contains several number of nuclei, so there will be a large number of magnetic moments, and these magnetic moments are randomly oriented in the absence of external magnetic field. From the figure it is clear they are randomly oriented, which are not oriented with the applied field. Okay, but in the case of but when we apply a magnetic field, these nuclear magnetic moments are either oriented with the applied field or oriented against the B0. From the figure, these three magnetic moments are oriented with the applied field, but these two are oriented against the applied field. If an external magnetic field is applied, the number of possible orientations can be calculated by 2I plus 1. For hydrogen nuclei, which has a spin quantum number of I is equal to half. So, the possible orientations with respect to the applied field is given by 2 into 1 by 2 plus 1, that is equal to 2. That means the hydrogen nuclei can have, the magnetic moment of hydrogen nuclei can have two orientation with respect to the applied field, and it is designated as plus half and minus half. These are the figure. The first figure, the nuclear magnetic moment. This is the nuclear magnetic moment, which is the resultant of the precessional motion of the hydrogen atom, and this magnetic moment is aligned with the applied field, and it is represented by plus half, and which is the lower. In each orientation corresponds to an energy state, so plus half corresponds to an energy state which is the lower energy state. And in the second one, due to the rotation of the nucleus, positively charged nucleus, which also create a magnetic moment, and this magnetic moment is opposed to the applied field, and it is designated as minus half, and this also represents a energy state which is a higher energy state. So, if a proton is precising in the aligned orientation, it can pass into the opposite orientation by absorbing energy. And from the higher energy opposite orientation, it's come back to the lower energy aligned orientation by losing the energy. And the transition from one energy state to the another is called the flipping of proton. From the figure, it is clear that this is the two energy state. One is corresponds to I is equal to plus half, which have lower energy, and it is not denoted as alpha state, and the other one which is a higher energy state, and it is denoted by I equal to minus half, which is called beta state. These are the two states, and these two states are degenerate in the absence of the applied field. But when we apply a external magnetic field, the two energy states splitted up. One will be lower energy and other will be higher energy, and the nuclei can pass from the lower energy state to higher energy state by the absorption of electromagnetic radiation in the radio frequency range, and it can also flip back to the lower energy state by emitting the radio frequency. And the emitted radio frequency is detected by the NMR instrument, and this emitted radio frequency is plotted against the intensity. This is the spectrum or NMR spectrum result. So intensity is plotted against frequency, and NMR spectrum is a plot of intensity of NMR signals versus magnetic field in reference to the TMS. Okay. And also about the technique. This technique consists of exposing the protons in an organic molecule to a powerful field, and the protons will precise at different frequency. We know that the molecule contains several number of nucleus. There will be some of them will be NMR active and other will be NMR inactive, and NMR active nucleus will begins to precise at different frequencies. Now we irradiate the precising protons with a steadily changing frequency in the RF range and observe the frequency at which the absorption occurs. But it is more convenient to keep the radio frequency constant, and the strength of the magnetic field is constantly varied, and at some value of the field strength, the energy required to flip the protons matches the energy of the radiation the absorption occur, and each absorption gives to a NMR signal. And that is why if the precising frequency of the proton matches with the intensity or the energy of the radio frequency irradiated or absorbed, such process is called nuclear magnetic resonance. So, it may be noted that all protons do not absorb at the same applied field. but the absorption depend upon the magnetic field which a particular proton feel. Clearly, the effective field strength is different for different set of protons, as one set of protons will have slightly different environment from any other set of proton. Thus, at a given radio frequency, different protons will require slightly different applied field strength to produce same effective field strength, which causes the absorption. Now we discuss about the effect of magnetic field. The frequency needed for resonance and the applied magnetic field strength are proportionally related, as nu is proportional to B0, where nu is the frequency absorbed of frequency of radio waves absorbed and B0 is the applied field. These are directly proportional. That means when we increases the applied field strength, the radio frequency, the frequency of the radio waves absorbed will also increases. Stronger the magnetic field, larger the energy difference between the two nuclear spin energy states and higher the nu needed for the resonance. The figure understood. From the figure it can be understood. These are the here the yellow line represent the two energy states corresponding to the proton, and in the absence of the applied field these two energy states are degenerate, but when we apply a applied field strength, the two energy states splitted up and one will be lower and other will be higher, and the energy difference between these two energy states, this is alpha state and this is beta state. Alpha state is for alpha state, the nuclear magnetic moment resulted due to the precizing motion of the proton will align with the applied field, and for beta state, the resultant nuclear magnetic moment will be opposed to the applied field, and the energy difference between these two states is called delta E. And when we irradiate the molecule with a specific radio frequency, and if it matches, and if the energy of the radio frequency matches the energy difference between these two states, an absorption occurs, and the absorption gives to a NMR signal. So if we increases the field strength, the energy difference between the two energy states also increases. It will increases the energy of radio frequency absorbed in order to occur a transition or to give a NMR signal, and this will give the frequency of radio waves we absorb to effect the transition, and it is given by nu is equal to gamma to mu h0, where gamma is gyromagnetic ratio and it is a constant which is different for each atomic nucleus, and nu is the resultant magnetic moment and h0 is the strength of the magnetic field, and this equation is called the Larmor equation, and this frequency is also known as Larmor frequency. So Larmor frequency is the frequency of the incoming radiation that will cause a transition.